Right now, within arm's reach of most people watching this, there's an aluminum can, maybe cold and full, maybe empty, on your desk. You've crushed hundreds of them without a second thought. But that thin metal shell is one of the most refined pieces of engineering you'll ever hold, and almost nobody knows how it's actually made. Let's start with what it's even made of. Pick up a can, and it feels like a single material, but it's actually two different aluminum alloys doing two different jobs. The body and rounded bottom are made from alloy 3004 or 3104 in a hardened H19 temper. The lid, the flat end with a tab, is made from 5182, a stiffer alloy with more magnesium so it resists buckling under pressure. Two metals, chosen for two very specific tasks. But where does the aluminum itself come from? It starts as bauxite, a reddish ore dug out of the ground. Bauxite is refined into a white powder called alumina, and then that alumina is split into pure aluminum metal and oxygen, using the Hall-Héroult process, passing enormous electric currents through molten material. It is staggeringly energy intensive. In a very real sense, aluminum is solidified electricity. Hold on to that idea. It becomes the whole point at the end. So how did we end up drinking out of this stuff? For most of the 20th century, drinks came in glass bottles or heavy steel cans. Then, on January 22, 1959, Bill Coors and a team of more than 100 people in Golden, Colorado, unveiled a two-piece, all-aluminum can, a 7-ounce Coors Banquet. It was light, it chilled fast, and crucially, it was recyclable. That first can was made by impact extrusion. The real revolution came in 1963, when the Reynolds Metals Company introduced the draw and wall ironing process, the method still used to make virtually every can today. By 1967, both Coca-Cola and Pepsi had switched to all aluminum cans, and the numbers exploded. U.S. can shipments went from 500 million in 1965 to 8.5 billion by 1972. So how does a flat sheet of metal become that perfect cylinder? It's one of the most satisfying manufacturing sequences in the world. It begins with an aluminum ingot about 30 inches thick. That ingot is rolled again and again until it becomes a thin coiled sheet. From that sheet, a press punches out round blanks about 5.5 inches across, and in the same motion, draws each one into a shallow cup, roughly the size of a hockey puck. This machine is called the cupper. The leftover sheet, a skeleton full of holes, is collected and sent straight back to be recycled. Then comes the star of the show, the body maker. The cup is pushed by a punch, first redrawn to a narrower diameter, then rammed through a series of ironing rings called dies. Each die is slightly tighter than the last, squeezing and stretching the wall thinner and taller with every pass. In a fraction of a second, a stubby cup becomes a tall, thin-walled can. At the bottom, a forming die presses that distinctive concave dome into the base. Fresh from the body maker, the top edge is uneven, wavy little peaks called ears, so a trimmer shaves off about 1/4 inch to leave a perfectly level rim. Next, the can is washed, dried, printed with its label, and critically sprayed on the inside with a thin epoxy or polymer lacquer so the drink never touches bare metal. Finally, the open top is necked, squeezed inward through many gentle stages, narrowing, say, a 211 diameter body down to a 202, so a smaller, lighter lid can be sealed on. The lid, made separately from that stiffer 5182 alloy, gets its tab and score line and is seamed onto the filled can at the bottling plant. Now, why does any of this actually work? Here's the part that should amaze you. After all that ironing, the sidewall of a can is around 1/10 of a millimeter thick, about the width of 2 human hairs. And yet, a sealed can hold internal pressure up to around 90 psi, roughly 3 times a typical car tire. The secret is in the metal and the shapes. Ironing doesn't just thin the wall, it work hardens the aluminum, aligning its grain structure and making it far stronger than the soft sheet it started as. The cylinder is the ideal form for spreading pressure evenly around its walls, and the concave dome on the bottom works like an arch, resisting the outward push of a carbonated drink instead of bulging. That's exactly why the lid uses the harder 5182 alloy at more than double the thickness of the wall. A flat panel has to fight pressure that the curved body handles naturally. The interior coating matters too. Aluminum reacts with acidic, salty drinks, so that microscopically thin lacquer is the invisible barrier protecting both the metal and the flavor. Now multiply all of that. Globally, we make roughly 180 billion aluminum cans every single year, which makes the humble beverage can the single largest use of aluminum on the entire planet. To hit those numbers, the machines move at almost unbelievable speed. A single body maker punches out somewhere between 225 and 375 cans a minute, and a full production line runs many of them in parallel, producing on the order of 500 to 700 can bodies every minute. During ironing, the metal and dies are flooded with a recirculated coolant because the friction generates so much heat that without it, the wall would tear. At that speed, how do you catch a bad can? Every can must hold pressure without a single leak, so the line runs constant checks. One key test is the interior coating. Cans pass through a device that applies a small voltage and measures the electrical current. Bare aluminum conducts. A fully coated can does not, so any gap in that microscopic lacquer shows up instantly as a spike in current. Cans are also checked for wall thickness, for pinholes, and for dome strength. The base is pressure tested to make sure it won't reverse and pop outward. And trimming those wavy ears isn't cosmetic. An uneven rim won't seam cleanly to the lid, and a bad seam means a leak. Reject cans are pulled and, of course, melted straight back down. Which brings us back to that ingot made of solidified electricity. Here's the payoff. Making aluminum from raw bauxite ore takes enormous energy, but melting down a used can and making a new one uses about 95% less. Recycling essentially skips the entire brutal smelting step. That's what makes a can unique. It's genuinely, endlessly recyclable. A can you drop in a bin can be melted, reformed, refilled, and back on a store shelf in as little as 60 days. In 2023, about 43% of US cans were actually recycled, below the long-run average. A reminder that the loop only works if we close it, but still the most recycled drink package there is. So think about everything packed into that shell. 2 precision alloys. A wall thinned to 2 human hairs, work hardened to hold 90 psi. A domed base shaped like an arch, formed by dies firing thousands of times a minute. An invisible coating tested with electricity. And the metal itself may well have been a completely different can just 2 months ago. The most ordinary object on your desk is quietly one of the most extraordinary things ever mass-produced.